Good morning. Today we are going over our practice exam 4. This exam has about 25 questions on it. There's a lot of math and it should be a good time. So let's get started. First question we have here talks about a gas, and it tells us we've got 31.7 liters at 2 atmospheres pressure and 27 degrees Celsius. We want to know what the volume is if the pressure was decreased to 1 atmosphere and the temperature remains unchanged. Now I told you I wouldn't give you the individual gas laws, but you can figure out what they're looking for if we use our combined gas law, P1V1 over T1 equals P2 V2 over T2, and they're telling me the temperature remains unchanged. So I actually don't even need the T2 and the T1 because I'm at a constant temperature. It remains unchanged. So P1 V1 equals P2 V2, that's Boyle's law, and we can plug this in here if we've got 31.7 liters. It's my initial volume. 2 atmospheres as my initial pressure. 1 atmosphere is my final pressure, and they're solving for V2. I'm going to divide both sides by 1 atmosphere. So 2 atmospheres times 31.7 liters divided by 1 atmosphere gives me V2, which should be 63.4 liters. Not so bad. Let's see. If I transfer a sample of gas at 17 degrees Celsius from a volume of 4.26 liters and 1.1 atmosphere to a container at 37 degrees Celsius that has a pressure of 1.10 atmospheres, what is the new volume? Look, the pressure is the same. So what I'm actually looking at here, I don't need the combined gas law, but just again to show you, pressure is the same, so that cancels. You could actually plug the pressure in, it just is unnecessary. Won't change the answer you get, but we get V1 over T1 equals V2 over T2, and we're calculating for V2, so I'm going to multiply both sides by T2. So that cancels, and we see that T2 V1 over T1 is equal to V2, and I do need to convert these to Kelvin. So if my initial temperature was 17 degrees Celsius, goes on the bottom, that's 17 plus 273.15. My final temperature is 37, that's going to be 37 plus 273.15. And my initial volume was 4.26 liters. Plug that in. I get a new volume of 4.55 liters, right there. Next, I have a sample of helium. I'm given this volume, this temperature, and this pressure. Now I change the temperature and I change the pressure and I want to know the new volume. Here's where I'm going to use the whole combined gas law. P1 V1 over T1 equals P2 V2 over T2. If I'm solving for volume, I'm going to multiply both sides by T2 over P2. By doing that, my T2 cancels, my P2 cancels, and I see that V2, which is what I'm looking for, is T2 P1 V1 over P2 T1. So T2, my second temperature, is 22 degrees Celsius, so 22 plus 273.15. My initial pressure, 740 millimeters of mercury. And my initial volume is 480 milliliters divided by my final pressure, 625 millimeters of mercury, and my initial temperature, T1, 47 plus 273.15. And I can plug all this in. Multiply that by 740, multiply that by 480, divide that by 625, divide that by 47 plus 273.15, and I get a new volume of 524 milliliters. Note here, millimeters of mercury cancel. Those are both going to be in Kelvin. So Kelvins cancel. So the milliliters is what remains behind right there. Now, question 4 says, what's the volume of a helium balloon that contains 3.26 moles helium at 27 degrees Celsius and 1.1 atmosphere? I don't have initial and final conditions, so I have to use just the ideal gas law here, which is fine. PV equals nRT, and they want volume, so I'm going to divide both sides by P. So V equals nRT over P. N is number of moles, that's 3.26. R is 0.0821 liter atmospheres per mole K. T is 27 degrees Celsius, 27 plus 273, that's going to make it Kelvin. And finally, 1.1 atmospheres on the bottom, that's my pressure. And we're just going to do a units check. Moles divided by moles cancel. Kelvin divided by Kelvin cancels, and atmospheres divided by atmospheres cancels. I'm left with units of liters. That's exactly what they're asking for. So I can just plug it in. 3.26 moles times 0.0821 liter atmospheres per mole degree Kelvin times 27 plus 273.15 Kelvin divided by 1.1 atmospheres leaves me with 73.0 liters. And just a reminder, I do give you the ideal gas law. I do give you the value for R. You don't have to have those memorized. Question 5 is the same type of question. Except that now they gave me the pressure in millimeters of mercury. So that's going to take me an extra little step to convert between millimeters of mercury to atmospheres. Again, that's given to you on the test. So you don't have to memorize that 1 atmosphere is 760 millimeters of mercury. So let's do that. 1520 millimeters of mercury, 760 for every 1 atmosphere gives me an actual pressure of 2 atmospheres. All right, so PV equals nRT. They want us to calculate the volume. Every question so far has been asking for volume. Okay, so N is 5 moles. R, 0.0821 liter atmospheres per mole Kelvin. T, we have to convert that to Kelvin, so that's 120 plus 273.15 Kelvin divided by 2 atmospheres. Moles cancel, atmospheres cancel, Kelvins cancel. We're left with liters, which is what they're asking for. 5 times 0.0821 times 120 plus 273.15 divided by 2 atmospheres gives me 80.6 liters. Next, what volume of NH3 gas at 1 atmosphere and 0 degrees Celsius is produced by the complete reaction of 0.416 moles of water according to this following reaction? Now, this question is putting together what we know about the ideal gas law and what we know about reactions. So I can plug in PV equals nRT and solve for volume. I've done that lots of times. Done it lots of times on this test so far. Volume is going to be nRT over P, but they want volume of NH3, So we need the number of moles of NH3. We need the temperature that NH3 is at. We need the pressure that NH3 is at. So that's fine. They tell us the pressure is 1 atmosphere. They tell us the temperature is 0 degrees Celsius. But they don't give us the number of moles of NH3. They give us the number of moles of H2O. So that's our first step. How do I get to moles of NH3 if I start with moles of H2O? That's not too bad. I know how to do that. I did that on the last test. If I have the balanced equation, which, look at this, I do, I can see that 6 moles of H2O react to form 2 moles of NH3. 6 moles H2O, 2 moles NH3, moles of H2O cancel, and I can calculate that I will produce 0.139 moles of NH3. And that's what I'm going to put here. Okay, so 0.139 moles of NH3 multiplied by R, which is 0.0821, multiplied by the temperature, which is 0 degrees Celsius, plus 273.15 to make it Kelvin, divided by the pressure, which is 1 atmosphere. And I see that I get 3.1 liters of gas. Now, if you did this previously and you got 9.3, that means you did all of this plugging in correctly, but you used the number of moles of water here rather than doing that conversion first. So be careful with that. You're going to have a question like this on the test where you have to do a multimole conversion before you can plug it in. You need to recognize that. Next, we're looking at the kinetic molecular theory. How are we explaining this observation that we can make a gas take up less volume? And some of these might not be true. Some of these might be valid assumptions of the kinetic molecular theory, but we're looking for the one that explains why can gases be compressed. And looking at each of these, the best one is to say this one, because the space between the gas molecules is much larger than the particles themselves. And it's that space, which is essentially empty, that is compressed. So that's the one that they're looking for. The rest of these really are all tenets of the kinetic molecular theory, but they don't explain why you could compress a gas. Next, we've got a mixture of gases, nitrogen, oxygen, and helium. We've got a total pressure, and we're looking at several partial pressures, so we want to know what is that for the helium. Well, we know that the total pressure is the sum of the partial pressures. So the P total pressure in a mixture of gases is the sum of the partial pressures. So that's the sum of the pressure exerted, in this case by the nitrogen, plus the pressure exerted by the oxygen, plus the pressure exerted by the helium. They tell us the total pressure is 760, and they tell us the pressure from the nitrogen is 90, and the pressure from the oxygen is 270, and they want to know what the helium is. I can do that. It's going to be 760 millimeters mercury minus 90 millimeters mercury minus 270 millimeters mercury means the remaining 400 millimeters mercury worth of pressure must have come from the helium. All right, why does water boil at a lower temperature at high altitude? It is because the atmospheric pressure is lower. So water is going to boil when the vapor pressure of the water is equal to the atmospheric pressure. Since the atmospheric pressure is lower, you get that vapor pressure equal to it at a lower temperature. since the vapor pressure is directly related to the temperature of the water, as we increase the temperature of the water, we increase the vapor pressure. At some point, that vapor pressure is equal to the atmospheric pressure, and since the atmospheric pressure is lower at high altitude, then that point comes earlier. Next, which process is exothermic? That's going from a higher energy state to a lower energy state. Gases are our highest energy state. Solids are our lowest energy state. So going from a gas to a liquid, that's higher energy state to a lower energy state. That's going to have to release energy in order to make that transition. These are the lowest energy state, going to higher energy states. And relative to gases, liquids are lower energy states. So all of these are lower energy states going to higher energy states. The amount of energy involved in melting a substance without changing the temperature, that's the heat of fusion. Fusion is that process of melting and or freezing. Heat of fusion is going to reflect that process. Water can be used to dissolve which types of compounds? Since water is polar, it's going to go with polar compounds and ionic compounds as well, which have charge. So we actually want both polar and ionic compounds. Which statement comparing solutions with pure solvents is not correct? Let's see. A solution containing solute has lower vapor pressure. That's true. Solution containing a solute has a lower freezing point. Yes, freezing point goes down and boiling point goes up. That's true. Here, the boiling point does not go down. The boiling point goes up. So we get boiling point elevation, freezing point depression, and depression of vapor pressure as well. And solution has a greater mass than an equal volume of pure solvent. That's true because the solute tends to fill in gaps between the solvent. And so your volume doesn't change appreciably, but your mass will. And now we're on to the math section of our solutions. And what we've got here is asking about concentration in terms of molarity. And we have done a dilution. So the equation we're going to use, and I don't give you this equation, so you're going to need to know it. The equation is our C1V1 equals C2V2, and they want to know the new concentration. So we divide both sides by V2, and C1, initial concentration, 6 molar. V1, initial volume, 50 milliliters. V2, final volume, 200 milliliters. Milliliters cancel, and we're left with concentration in units of molarity, 1.5 molar, right there. How many milliequivalents of chloride ion are contained in a sample that has this many grams of chloride ion? So I have to recognize that 1 equivalent of chloride, since it has a -1 charge, is 1 mole of chloride ions, because it's only 1 charge. So we're looking at 1 charge equivalent. So then we look at the periodic table, we see that 1 mole of chloride ions weighs 35.45 grams. So if I have 0.725 grams of chloride, then since 35.45 grams of chloride is in 1 mole, and that every 1 mole has 1 equivalent of ions in it, and they want to know milliequivalents, not just equivalents. So we have to take that extra step and say that 1 equivalent of chloride ions has 1,000 milliequivalents of chloride ions. So our equivalents cancel. 0.725 divided by 35.45 multiplied by 1,000 gives me 20.5 milliequivalents. Here we're making a solution. They want to know molarity. Molarity is moles per liter. And they have kindly given us grams and milliliters, so we have to do some extra work here. But if I've got 10 grams of acetone, and I want moles, I need the molar mass. C3H6O is 3 carbons plus 6 hydrogens plus 1 oxygen, 58.08 grams per mole. It's going to go on bottom. Next, I've got 125 milliliters. Volume goes on the bottom. And I've got 1,000 milliliters in 1 liter. So now I have set this up so I have moles on top, liters on the bottom. Moles per liter is molarity, so I can plug this in. 10 divided by 58.08 divided by 125, multiply that by 1,000, and I get 1.38 molar solution. And this one is even easier. What's the molarity of a solution that has this many moles and that many liters? Should have asked me that one first. Moles divided by liters is molarity. So that's 0.077. And I don't know why they've got check boxes here because there's only one right answer. So that's it. How many grams sodium hydroxide needed to make 750 milliliters of a 2.5% weight per volume solution? Okay, you have to remember, and none of these formulas for concentration units are given. You have to know these. But the percentage is going to be, we always use grams or milliliters. If they want weight per volume, then they want the weight, the solute, per volume. That's going to be milliliters of solution. Multiply it by 100% to make it a percent concentration. So they want to know grams, they give us milliliters, so X grams divided by 750 milliliters, multiply that by 100%, and they want to make a 2.5% solution. So we solve for X, we do that by dividing both sides by 100%. So those cancel, and incidentally that percentage unit cancels. We'll multiply each side by 750 milliliters. So that cancels, and we'll get the number of grams. So 2.5% divided by 100% gives me a fraction of 0.025. Multiply that by 750. Means I'm looking at 18.75 or 19 grams of sodium hydroxide. What is the osmolarity of a 0.2 molar solution of KCl? Since they gave me molarity, I just have to remember osmolarity takes the molarity and multiplies it by the number of things which dissolve or dissociate. So if I was a covalent compound, osmolarity is the same as the molarity. If I'm an ionic compound, I split that up and I look at how many ions I get. And so since I get 2 ions there, that is 1 potassium ion, 1 chloride ion, then I take the molarity and I multiply it by 2. 2 ions gives me a 0.4 osmol solution. Question 20, concentration in parts per million. Concentration in parts per million is exactly like percentage, but instead of multiplying it by 100 to make it a percent, here I'm going to multiply it by 1,000,000 to make it a parts per million. So if I plug this in, remember I always need to use grams or milliliters, so I have to convert from grams and convert from kilograms. I'm going to say 450 milligrams becomes 0.450 grams. 150 kilograms is 150,000 grams. And multiply this by 10 to the 6 to make it a million. Fraction in a million, 0.450 divided by 150,000 multiplied by 1 times 10 to the 6th gives me 3 parts per million. This was a homework question too. And finally, the solubility of gases in liquids does what as the temperature increases, and does what as the pressure increases? So we might have memorized this, but if we didn't, then we could just stop to think about it for a minute. I've got a liquid, and I've got gas particles, which have lots of energy. They're running around, and I've got some of those gas particles dissolved in that liquid. And we've got this process, this dynamic equilibrium, where gas particles are dissolving into the liquid and they're dissolving out of the liquid. As the temperature increases, we know that the kinetic energy of gas particles increases. So it's going to be harder to keep them inside the liquid when they have so much energy. They're just going to want to escape. They'll have plenty of escape velocity. So as the temperature increases, the solubility of gases actually decreases. So the solubility of gases and liquids decreases as the temperature increases. But as the pressure increases, we increase the pressure of gas. We could do that by decreasing the amount of volume space or increasing the number of gas particles. That's just going to increase the number that happen to make it into the solution there. Or in other words, in the equilibrium, if we add some to this side, we're going to get more on this side. So the solubility is going to increase as the pressure increases. So decreases as the temperature increases, increases as pressure increases. So we're looking at this one. And if you think about this from kind of a commonsensical point of view, if you have something like a bottle of soda that you bought and you took off the lid so that you could let stuff escape and you put it in the fridge, or if you put it in the hot sun, I think you would recognize it probably go flat faster in the heat than it would in the cold. And additionally, the way that they get the carbonation in there in the first place is by putting it under a lot of pressure, which is why when you take off the lid, there's always that little sound where it's releasing some of that extra pressure from the carbon dioxide on the top. All right, that is all. I think we selected an answer for each of these. And so let's submit this. See how well we did. Excellent, we did well. So I hope this was helpful, and I wish you guys luck on the exam. Have a great day.